Hey guys, Mr. Betts here. Let's take a look at a few examples of how we're actually going to use this linear approximation. So first example here, we're going to use the line tangent to the curve f of x equals sine of x at x equals 0 to approximate sine of 0.1. And then we're going to confirm that our answer makes sense so that it's a pretty good approximation using our calculator and see how accurate it is. So the first thing we want to do here is we actually want to write the equation of the tangent line. So it says write the equation of the tangent line and use it to approximate the value of this function. A problem might not always be this explicit. It might just say use a linear approximation to approximate this, but the same idea is going to apply. We're writing the equation of a tangent line. So at x equals 0, f of 0 is 0, so the sine of 0 is 0. So that gives us our point of tangency at 0, 0. And then we need to know the slope of the curve at that point. So f prime of x is going to be cosine of x, and f prime of 0 is going to be cosine of 0, which is 1. I do want to point out here, just be careful about your notation. We don't want to write this is equal to 1 here because f prime of x could work for any x value, so we don't want to plug in a particular x value when we have x there. So this is going to give us our slope. And so the equation of the tangent line is going to be y minus 0, which is just y, equals the slope times, so 1 times x minus 0. So it's actually just y equals x is the equation of the tangent line. So the next thing I'm going to do is I'm going to plug my point where I want to approximate the function in for x in this. So this is a pretty straightforward one. We plug this in and we get 0.1. What that tells us is the value of the sine curve at 0.1 is close to this. So to write that answer out mathematically, I want to say the sine of 0.1 is approximately equal to. So right off the bat, when we were asked to approximate sine of 0.1, I know that my answer is going to be in this form. Sine of 0.1 is approximately equal to. This is an important thing to use here, this approximately equal to. We do not want to say the sine of 0.1 is equal to. All right, this is an approximation method, so we need to show that we know it's an approximation, and it's just approximately equal to the value that we got here. So sine of 0.1 is approximately equal to 0.1. Now, before I plug this in my calculator, I want to think about whether this is going to be too big or too small. So if we think about our sine function, so sine function is going to look like this. Our tangent line at x equals 0 is going to look like this. And we are using the line to approximate the function. And to the right of 0 here, the sine curve is concave down, which means the curve is going to be below the line. And so the value of sine is going to be below the value that we got from the line. So this is going to be the value of the function is going to be below this. So this is going to be an over approximation. So the value of the sine of 0.1 is about 0.1, but we actually know it's a little bit less than 0.1 because the sine curve is concave down on this interval. If we plug sine of 0.1 in our calculator, make sure that you're in radian mode when you do that. Sine of 0.1 is approximately 0.1. That's our answer from the linear approximation. And we can see from our calculator that we get a value that's really close to 0.1. Rounded to the nearest thousandth, it's only off by 2 thousandths. So for practical purposes, a lot of times this might be good enough for some sort of construction project that we might do or some sort of engineering project that we might be doing. Next question is really similar, except just a different function. So function's e to the x, and we want to approximate the value of e to the 0.1. We do know the value of e to the 0, so that's why we're using that as our point of tangency. So f of 0 is 1, because e to the 0 is 1. F prime of x is e to the x, so f prime of 0 is going to be 1. So we have our point, which is at 0, 1. We have our slope. And so we write the equation of the tangent line, y minus 1 equals the slope times x minus 0, which means that our linear approximation, we're using the tangent line as our linear approximation, is going to be y equals x plus 1. We actually saw this in the introduction video. The line tangent to the e to the x function at x equals 0 is y equals x plus 1. So then to approximate e to the 0.1, we're going to plug 0.1 in here, and we get, so 0.1 plus 1 is 1.1. This I don't actually have to write, so I'm plugging it into this expression here. So I'm going to write e to the 0.1 is approximately equal to 1.1. So that's our answer. Again, we got that by plugging 0.1 in for x there. And let's think over and under approximation again here real quick. So the e to the x function is going to look like that. It's concave up. We are using the straight line approximation, which is going to be below. So this is going to be below the actual answer. So this is going to be an under approximation. So we should expect the actual value to be a little bit bigger than this. And when we plug it into the calculator, we can see that it is just a little bit bigger than 1.1. It's off by just a little over 5 thousandths. So again, for practical purposes, this would be a pretty good approximation. Now, I mentioned in the introduction that the closer to the point of tangency we are, the more accurate our answer is going to be. So instead of approximating e to the 0.1, let's approximate e to the 0.01. So our tangent line is still y equals x plus 1. I'm not going to go through all the steps for finding that. So e to the 0.01 is going to equal 0.01 plus 1, or 1.01. And I use an equal sign where I said we shouldn't. I do want approximately equal to here. I do want to point out, though, that we should use an equal sign right here, because it's saying that this expression is equal to this expression, which is true. Again, this is a concave up function, so our linear approximation should be a little bit too small. However, where the 0.1 approximation was off by 5 thousandths, this one is off by 5, what would that be? Tenths, hundredths, thousandths, 10 thousandths, 100 thousandths, millionths. So this approximation is only off by 5 millionths. So for practical purposes here, if we were building something and we're off by 5 millionths of even a meter, we're really, really, really close to the actual value. So this approximating method can be very useful, especially if we are building things, constructing things, engineering things.